Hello, my name is Jason Del Aguila. I teach at Highland High School in Palmdale, California. In this video, well, this is what I look like. Uh, and in this video, I'm going to be showing you some volume activity that you can do in Calculus AB class after talking about revolution solids. And here we go. In this activity, we're going to be finding the volume of one of these objects. So I just went to the store and got some, well, like gas station, got some bottles, went to Bevmo, got some things, and these glasses. Also the gas station. Just get some containers. The weirder the shape, the better. Just it makes it more interesting. We're going to use calculus and revolution solids to find the volume of one of these objects. For this video, I'm choosing to use the cocktail glass. So let's see what materials you need. I wrote them down right here. You need the bottles or containers. When I did this in my calculus class, I gave them, or I set these out at the front of the class and put them in groups of two, and they got to choose whichever one container that they wanted to predict the volume of. You can get more of these so that more people can use them all at once, but first thing you need are those containers. Measuring cups that measure in milliliters. One measuring cup that was marked every 50 milliliters that goes all the way up to 500, and then another smaller measuring cup that measures by, I think it's 10 milliliters, just to get more accurate measurements. Some centimeter graph paper, because when you cube a centimeter, it becomes milliliters. That way when we get the volume, we can measure them out in our measuring cups. So the centimeter graph paper is important. The instructions, the instruction sheet that I made up, you can change it or use whatever version you have, but this is what I mean by that, predict the volume. Writing utensil, of course, something to write with, and a computer with Microsoft Excel, and maybe Wolfram Alpha. They could do this on their graphing calculator as well, but Wolfram Alpha makes it really, really quick and easy. I think that's all the materials that you need. If not, I'll mention it as I go. So the first thing that I am going to do is I'm going to choose this, and if I were a student, I would go up to the front of the class, pick up this cocktail glass, and I would get my graph paper, my centimeter graph paper, and I would trace it out. So that's what I would be doing here. I'd hold it so that the inside of this starts at, whoops, for sure, man. Hopefully it doesn't say anything inappropriate. The inside of this glass starts at the, I don't know, the first line of my graph paper, and that's kind of hard to do because it distorts the picture, but I would line it up nicely, and then I'm going to trace it. So I would take my pen or pencil, I used a pen for this, and I'd trace along the outside. Something to notice though is the pencil or pen is kind of thick, and there's also a thickness of this glass that you have to adjust to. So what that looks like, I mean, I traced the very, very outside line is my first trace. And I traced all the way on the outside of the glass, and then I adjusted for the length, or I mean the thickness of the pen. That was kind of a guess. This is the part where it's just estimation. And then I also made it a little bit smaller just based on the thickness of what I thought the thickness of the glass was. Usually between this top line and the actual inside of the glass, maybe it's around a pencil thickness. But I adjusted that. And these are all in the instructions as well. I adjust my trace, and then I put ordered pairs every centimeter. So I'll label this 1, 2, 3, so forth, and then put points on every centimeter. So what does that look like? That's this. So I labeled my graph, and this is all the students, they can do this. I labeled it 1 through 4 up here because it doesn't go any fatter than that. And then I listed out my ordered pairs. The x-coordinates are, of course, on the x-axis, and then the y-coordinates are on the y-axis. And after I've listed out all of these ordered pairs, I'm going to use Excel to fit a curve to these ordered pairs. So that way I can have an equation. Once I have an equation, I can integrate using the disk method to find the volume of revolution. And that's exactly what I'm going to do right now. Excel. So where's Excel? I think this is it. Yes. So I have already put in those ordered pairs because I don't think you want to see me type them in, but they're the same as in this picture. So these ordered pairs, I already typed them in, and this is how you fit a curve to these ordered pairs. The x coordinates are in this column, the y coordinates are in this column, and I'll just select, drag my mouse over, select all of those, and then go to Charts, Scatter. I want to make a scatter plot of this, so mark scatter plot, and it makes a scatter plot for me. I want to kind of make it look like the length of the bottle, so I'm going to stretch it out a little bit. That kind of looks like our bottle, right? Or not a bottle, cocktail glass. And then I'm going to fit a curve to this. So how do I do that? Well, I select one of the data points, and then all of them get selected, except for this last one. That's weird. And now they're not getting selected. So I select them. It selects a lot of data points, and it'll use these to create a trend line. So to do that, I right-click, add trend line, and there's some important things about this. I'm going to make it a polynomial. You can choose a bunch of different things based on what you think your shape is. Maybe that martini glass would actually fit a logarithmic shape, a logarithmic graph because of the way the shape is. I don't know. Choose whatever you think is best, and I'm just going to choose polynomial because it's a little bit curvy, and I can change the order of the polynomial. That way my line fits better. And I'm just going to use whatever looks the best. So I'm just going to change it until I feel like it's good. 4 seems pretty nice. 5 I guess is nice. I like 5 the best actually. Maybe 6. Excel only gives you the option to go up to a 6-degree polynomial. So this, I think I'll stick with 5. I like 5 the best. So we have that. We have our graph. Go to options. This is not too important, but I just want to make it readable. Cocktail trend line. And then I guess I can force it to start at the 0. That's not necessary. In some of the actual other objects, you might not want it to start at 0 because the bottle has a flat bottom. This has a curved bottom, so maybe not that. Display the equation on the chart. That's very important. We're going to use this equation. And just to make my line pop out a little bit, I'm going to change it to red. That's just by going to line, changing it to red, making it a little bit thicker. I don't know, looks better to me. You can have your students print this out. If you're in a computer lab and you have paper, why not? It looks cool, and I don't know, it's something that looks better to parents if they take it home and show what they did in class. So I have my trend line. I have my equation for my trend line. I think I'm good. Here's the big problem. This trend line, or this equation, if I were to plug in an x value that's like 12, I actually wouldn't get, I don't know, something near 2.7, 2.6. I wouldn't get that. This equation is not accurate enough. And through a lot of troubleshooting, I found out how to make it more accurate. So if this is what you do. You select your equation, so select it by just clicking on it. Go to Format, Trendline Label, and then go to the numbers, so like the number section. So it's going to format these numbers. These don't have enough decimal places. The more decimal places that I have, I'm just going to let it be a number. I could use scientific notation, but I'm just going to use a regular number. I don't care how messy it looks. Instead of 2 decimal places, I'm going to see how many decimal places I need until, well, let's see. Here, I still have numbers at the very end, I don't know if you can see that or not, but I'm going to keep going until I run out or until I have repeating zeros. So here in the x term, I have repeating zeros already, repeating zeros, repeating zeros, repeating zeros, but this one's not done yet. So I'm going to keep going until this one has repeating zeros. So 19, still not. Oh, yeah, there's repeating zeros there. Now all of them have repeating zeros. So I'll just back it up a little bit. down to 20. I still have a ending 0 there. So 19. I needed 19 decimal places. This step will be different depending on whatever object you picked, but it's very, very important. For this equation to be accurate, you need a lot of decimal places. They're not going to integrate this by hand, so it doesn't really matter. So we have that, and I think that looks good. I think that's all we need. I'm going to try and move it over just so we can see it better. And there we go. We have an equation for this trend line. And now we can integrate it using our methods for finding volumes of revolution, and then we'll test it out. We'll see how close we get to actually filling up the cup. Yeah, just in case you can't see this, I'm going to copy and paste it into a Word document. I don't think you'll have any trouble, but there you go. That's what it is. It's not very pretty, but I don't have to type it in. So what I'm going to do is I'm going to use Wolfram Alpha to calculate my integral. So I'll go over to Wolfram Alpha, wolframalpha.com, and I'll just tell it to integrate from, where are my limits of integration? I know that I start at 0 and I go all the way to 16 as shown by my x coordinates. So from 0 to 16, integrate from 0 to 16. And what I want to be integrating, the integrand, remember to find the volume of revolution, you have to multiply by pi, and then times my equation, and I have to square that. That should take care of it. I just need to type in my huge equation, my equation from that. Well, I already have it copied, so I'm just going to paste it in there. I just have to be careful because I have the y equals here out in front, so I got to get rid of that. So now I have pi times the radius. This is for the disk method. Yeah, disk method. Radius squared. Wolfram Alpha should notice that this is supposed to be an exponent. Wolfram Alpha is pretty cool that way. So let's see. I'll hit calculate and we wait. We just sit here and wait. It tells you what you were trying to put in, but it writes it with good notation. It does recognize them as exponents, and this comes out to be 427 cubic centimeters, which are milliliters. So there's my volume, and I would tell the kids actually on the instructions. Where are they? On the instructions here, it says calculate the volume, write down your volume. I asked them to write down their integral as well, so they're going to have to write out that huge long equation, just so I can maybe double check it if I suspect anything. They write down what they calculated, and then they test it out. So here we are. We have about 427 milliliters, and right now I'm going to try and test it out. Let's see. I hope it works. I don't know. I'm pretty sure it worked because I did this before, but it's kind of cool just to see. So I have a bottle of water here. When it's 427, I have my big measuring cup. I'll go up to 400. I think it's backwards on this because I'm using Photo Booth. But I'll go up to 400, and then I'll measure the remaining 27, about just a little bit under 30. I'll measure that out. It's kind of wet inside. I'll measure that, and I'll pour it into here, and then I'll pour this into the cocktail glass and see how close I get. So right now, I'm trying to do 400 milliliters. And the Sobe bottle, it has no measurement. I just filled it up so I can not be at the sink. So, and then students would be doing this in class. It might get kind of wet, but it's just water, so hopefully no big deal. The first time I did this, the first people that tried, they got cheers. It was like they said, water, yay! They were excited about it. So it's something that they can engage in. So that's 400 exactly. And then here, I think it was 427, so I'm going to add it, or fill it up to just below the 30. I don't have, I have marks every 10 milliliters, so I just got to guess on this one. It looks like 22. That looks like too much. I want it to be close. I don't know. Still looks like too much. Whatever. Close to 30. Pour it into this, and then we'll see how close to the edge we get. This is just the fun part of the experiment. Hopefully it doesn't spill on my computer. In class, you can give them some kind of prize if they get closest. I offered them eternal glory. They didn't care for that. Whoa. Look at that. I could have hit a little bit more. My calculations was a little bit off. You can see there's barely a little lip around there, but it's pretty close. It's very, very satisfying. So that's the entire activity. There's more documentation I include, I think, in a file. If you need any files, you can just email me. And that's it. Kids have a lot of fun with this, and you can use calculus, and it's pretty cool. Thanks for watching. Peace.